Hello again. Now we're going to start talking about an example on network compression based on what we have learned so far about which activities to compress and how to achieve time reduction or time acceleration. So here we have an example. Calculate the normal, least cost, and crash durations for the following project and calculate the cost associated with each duration, whereas indirect costs are $120 per day. So the costs given here in this table are basically direct cost for each activity. It shows the activity, its immediate predecessor, normal duration and crash duration, which shows the amount of compressibility that the activity has. In addition to the cost, normal cost and crash cost, how much would it cost to compress this activity by that amount of time. So for example, activity A can be compressed by 1 day, which is the difference between the normal and the crash duration, at an extra cost of $100, which is the difference between the crash cost and the normal cost. And we have that for all the activities. Notice here, for example, that activity F has a normal duration of 4 days and a crash duration of also 4 days, which makes delta T for activity F equal to 0. Therefore, activity F is incompressible. If activity F ends up being a critical activity, it would be excluded from our efforts to compress that activity because it is incompressible in the first place. Same thing applies here to the delta C. It doesn't have any delta cost because again it cannot be compressed. So our first step is looking at this table, first of all building the network, and then looking at the delta T and delta C and the cost slope for the different activities. The total direct cost for this project can be obtained by adding the normal cost for all activities, which is equal to $4,950, which is basically the sum of these costs here, normal. Adding these costs, that's going to add up to $4,950. The total indirect cost can be obtained only by solving the network and multiplying the total duration by the indirect cost per day, which again is $120 per day. Therefore, we have to perform the forward pass, backward pass, and determine the expected early finish of that network. Multiply that time, the number of days, by 120, and that will give us the total indirect cost for this project before compression. So here's our network that we have drawn based on the information with the IPAs and so on, and it shows basically several paths. Here's one path, here's a second path, here's a third path, and here's the fourth path. So we have 4 paths to this network: A, B, E, H, A, C, E, H, A, C, F, G, and A, D, G. These are the 4 different paths to this network. So the next step is to perform our calculations. And here's a very simple display of these calculations. It shows the early start for activity A is 0, duration 5 days, so the early finish is 5, and so on. So it's a very simple calculation of the network time, which shows that this project is going to end on day 25. Therefore, this network expected to finish on day 25 has one critical path, which is going to be A, C, E, H, as it appears from the identical numbers on the early and late sides. So, and the total indirect cost is 25 times 120, 25 days times $20 per day, with a total of $3,000. We had already calculated the direct cost to be $4,950, so the total cost for this project before compression is $7,950. And here it shows the critical path that we talked about. So the next step is to draw the table to show the delta T, the delta C, the cost slope for the different activities. And here's the duration for each path, A, B, E, H. Now the duration for each path is assuming that the other paths do not exist. So if, for example, C did not exist, activity C did not exist, then the start date for activity E would have been 12, the start date for activity H would have been 18, and the completion date would have been 24. Same thing here. If the 2 top paths did not exist, or 3 top paths did not exist, and we had only A, D, G, then activity G would start on day 16 and end on day 23, and the project would end on day 23. That's how we determine the length of each path. Here's the table based on the calculations of the crash and normal durations and crash and normal costs. We obtain the cost slope, which is the difference in cost divided by the difference in time. So for the first activity A, 100 divided by 1, for B, 150 divided by 2, and so on. And we find, again, we remind that activity F is incompressible. Now the ones in red are the critical activities. So these are our primary candidates for compression. They have to be critical, compressible, effective, and among the critical, compressible, and effective activities, we will select the one with the lowest cost slope. Going back to this network here, we find that we do not have any start-to-start or any finish-to-finish relationships. It's a very simple network with all finish-to-start relationships. Therefore, all the critical activities are effective in compressing the project duration. None of the critical activities are none is incompressible. Therefore, again, all the critical activities are candidates. So the main criterion determining which activity to start with is going to be the cost slope. So looking at this table here, we look at the critical activities and the cost slopes. Activity A has $100 per day. Activity C, $40 per day. E, $50 per day. And H, $120 per day. Therefore, looking at this, we find out that activity C is the least expensive to compress. So this is going to be our primary candidate for compression. And that is compression cycle number 1. We're going to conduct these compressions in different cycles. As I mentioned several times before, the time compression or network compression problem is not a hard problem at all. The concept is very simple. It's just a repetitive calculation of the forward and the backward paths after each cycle of compression, compressing each activity by 1 day at a time, and then recalculating the dates for the network. So in cycle 1, compress activity C by 1 day. Now we notice that, looking at the network again, look at the total float on activity B. 13 and 12, so the total float for this activity is only 1 day, which means if I reduce the duration of this activity by 1 day, if I end this activity on day 12, going in the backward path, we're going to find out that the late finish for activity B is going to become 12, which means activity B is going to lose its first day or its only day of total float, which is going to make it a critical activity. So we're going to create a new critical path going through A, B, E, H. So this is the first cycle. Activity C is compressed and B will become critical. With the cost of compression is going to be $40. Therefore, to proceed with the second cycle, we have to check the cost slopes of activities to be compressed. Remember that in order to achieve an effective compression of more than one critical path, we must compress all critical paths by the same amount. So if we have multiple critical paths that need to be compressed, it's not enough to compress only one of them, because if you compress one and leave the others incompressed or uncompressed, that would make them longer and they would remain critical, whereas the one that has been compressed is not critical anymore. So in order to achieve that compression, we have to compress all the critical paths by exactly the same amount. And this can be achieved either by compressing one activity on each one of these paths by the same amount, or looking for a common activity that is shared by all of these critical paths and compressing this activity, which is going to result in a complete in a compression for all the existing critical paths. The net cost of compression here is savings of $80. Why? Because we have spent an extra $40 to compress activity C, but at the same time we reduced the total project duration by 1 day, which saved us $120 in indirect costs. And here's the calculation after the first cycle of compression. Notice that each cycle is going to be done in a different color so that we can identify which activities have been affected and which dates have changed. So here, when we compress activity C from 8 to 7, perform the calculations. In the backward pass here, I have activity B with 0 total float. Therefore, now we have a new critical path in addition to the old one. So ACEH is still critical, and now ABEH has become another critical path. Now let's look at the other paths. We notice here that activity G has a total float of only 1 day. So does activity F, and also so does activity D. Therefore, any additional compression to this path more likely is going to result in these activities becoming critical, except if we compress activity A, because compressing activity A is going to affect all the paths, so the non-critical activities are going to keep their total float. So now let's look again at the cost of compression. In order to compress this path, these two paths at the same time by the same amount, we can either compress activity A by itself because it's joint between the two, or we can compress activity E by itself, or we can compress activity H by itself. Therefore, A or B and C together, or H by itself, or E by itself, or H by itself. Let's look at the cost for this compression. So we find that activity C is still the least expensive, followed by E, followed by A, followed by H. Now, if I want to compress C, I have also to compress B at the same time. Therefore, the cost of compressing 1 extra day is going to be 40 plus 75. That would be 115 to achieve that compression. Or another option is to compress activity E by itself, or to compress activity A by itself, or activity H by itself. So based on the information from cycle 1, the least expensive activity to compress is activity E. Again, from here, from this table, least expensive activity to compress is activity E with a cost of $50. This results in converting all the activities on the network into critical activities, because again, all the remaining activities had only 1 day of total float. Once we compressed activity E, all of these non-critical activities will lose that total float, thus becoming critical. And the net cost of this compression is a saving of $70, because again, we spent an extra $50, we saved $120, so the net is savings of $70. And now we can see the new numbers, and it shows clearly that all the other activities have become critical. So here's the original critical path, here's the second critical path, and here's the third critical path. Each one shown in a different color that shows when did these activities become critical. That's very important, again, as we mentioned before, to use different colors so that we do not lose track of these changes and which activity was changed at which cycle, and so on and so forth. Now the project ends on day 23. So we have managed to reduce the duration by 2 days, while still saving some money, which is good. Our next step, again, all the activities now are critical, so we need to look at which activities need to be compressed. In order to compress this network, again, the options are, I have to compress all the paths by the same amount. So it's either compressing, for example, H with G, or E with G, or B and C together with D and G, because D is on the separate path from G. So remember that we have 3 paths. So it's either B, C, G and D together, or E, G and D together, or H, G and D together, because F is incompressible, or maybe looking at activity A, which is the common activity in all paths. If we compress activity A, that might end up being less expensive. So looking at the cost, A by itself is 100. BC with any other activity that already exceeds the 100, so that's not our choice. Therefore, we find out that the cheapest activity to be compressed is going to be activity A. Since we now have 4 critical paths, compressing the network requires compressing all the paths by the same amount. This can be achieved by compressing at least 1 activity on each path. And again, here it shows the analysis of the costs together. So by compressing activity A 1 day, the net cost would be a savings of $20, because the extra cost is $100 and the savings of $120. Now look at these numbers, 165, 200, 270, and so on. That is more than the 120 that I'm going to be ending up saving. Therefore, if I compress after compressing activity A, if I try to compress any other activities, that's going to be on the more expensive side, because that's going to end up costing me more money. So I'm not saving any money by reducing the duration, I'm actually spending more money. And here, once we have compressed activity A, all the activities are still critical. And now we end the project on day 22. So here it shows the different compression cycles that we have done and which activities became critical when. Now the question is where to stop. Are we going to keep compressing this network, or should we stop here? And the answer to this question depends on what's the objective we need to achieve. If we need to compress the network to the maximum, it is still compressible, because again, we can compress B and C and D and G, for example, at the same time, and that's going to result in another day of compression. So we can do that, but that's going to be, as we have already noticed, it's going to be on the more expensive side, because we are not saving any money by doing that. We are spending more money. If we need to compress the network until it's not economically wise to compress it any further, then we have to stop here, because again, compressing further is going to result in more expenses, and that's not economically meaningful. If we need to compress the network by a certain number of days, let's say all we wanted to do is compress the network by 3 days, we have already achieved that, so here we can stop. So it depends on how the question is being asked. So the question can be asked as compress the network to the maximum, regardless of the cost. In this case, we would keep compressing, or compress the network until it's not economically feasible or meaningful to compress it any further, which means we're going to stop as soon as the savings are not achieved, which means the cost of compression exceeds the savings resulted from reduction in indirect costs, or compress by a certain number of days. As soon as we reach that number of days, we're going to stop our compression. And this is basically a graphical representation of that concept. Here we have the direct cost curve, which shows that the shorter the duration, the higher the cost of direct costs. Here's the indirect cost, which shows the opposite. The shorter the duration, the lower the indirect cost. And then here's the sum of the two curves together. It's adding the numbers from the two curves together. It shows that for a certain portion, as you compress, the total cost goes down, which is what we have been doing so far. And then you reach a certain point and the cost starts rising up again. So this is where we had stopped originally right now in this problem. And this is going to be called the right side of the total cost curve, and this is the left side of the total cost curve. On the right side of the total cost curve, the indirect cost is more effective. So with the reduction, the total curve trend follows the same trend as the indirect cost, which is reduction as you compress. On the left-hand side, the curve, the total cost, follows the curve or the trend of the direct cost. As we compress, the total cost goes up. So again, until we reach a certain point where we cannot compress anymore. So this is basically, in a nutshell, how we can achieve network compression or time acceleration. I hope this helps you understand the concept, and you can practice on some additional problems. Thank you, and see you later.